Hello everyone, welcome back to a lecture series in Gated Data Science and AI. So in this lecture, we are going to discuss about the propositional logic, right? In the previous lecture, we have discussed about introduction to a logic. So in that, we have discussed about knowledge, what is sentence, what is syntax, and what is semantics of those sentences. So we have discussed all those things. So in this lecture, we are going to discuss about the propositional logic. Okay. Now, this is the same slide that we have discussed in the previous video. This is about the knowledge and this is about the sentences. And we have also discussed if we have given three sentences like this, but what we can conclude from this particular sentences. So see here. So first sentence is, if it didn't rain, Ravi visited Mumbai today. Ravi visited Mumbai or Goa today, but not both. And Ravi visited Goa today, right? By just looking at this particular three sentences, so what I can conclusion I can draw. So I can say that it was raining today, right? It was raining today, and Ravi visited Goa, right? Today, right? So it was raining today, and Ravi visited Goa today. So this is what I can say in short by just looking at these three particular sentences, right? So this is how, as a human being, I can understand these particular languages and I can infer from these particular sentences. But what about the computer, right? What about the AI agent, right? So what about AI agent? Do they understand this particular English language? No. So we need to convert this particular sentences into the understandable format, right? For example, for computer, they understand binary language, right? It's 0 and 1, right? So we need to convert these particular sentences in the format of 0 and 1 sentences, and they can draw the conclusion based on that. So for this purpose also we use logic part, that is propositional logic, right? And second one is predicate logic. Okay, so we are focusing on these two particular type of logic. This is what given in our GATE syllabus. Okay, and this is what we call knowledge representation, and inside that also it is logical representation, right? So logical representation of particular sentences we can say about the propositional and predicate logic. Okay, so I hope you understand this particular sentence, three sentences, and how I can draw this conclusion. If not, so you can watch the previous lecture. Okay, now let's discuss about the propositional logic. What is propositional logic here? So propositional is a declarative statement, right? It must be either true or false, but it cannot be both true and false, right? So we have discussed this in the previous lecture that 2 plus 2 equals to 4. This is my also sentence. 2 plus 3 equals to 4. This is also my sentence. But 2 comma 4 plus equals to 3. This is not a proper syntax, right? There is no meaning to it. So it is not a correct proposition, right? So it is not a correct one. This is true. So I can say it is true proposition. This is false. So I can say false proposition. So proposition can be true or false. It doesn't matter, right? It should be in proper syntax, right? So we use T to denote true and F to denote false. So generally in Boolean algebra, we use T for 1 and for F we use 0, right? This is the thing 1 and 0. Now examples of proposition. So what are the good examples of proposition? For example, John loves CSE 191. Yes. 2 plus 3 equals to 5. That is correct. That is true proposition. 2 plus 3 equals to 8. This is false proposition. But these are all other propositions, right? Sunrises from west. Yeah, this is also a proposition. So, but what are the examples of non-proposition? Does John love CSE 191? This is basically a question, right? So questions are not considered as a propositional, okay? Because we are not giving any particular information, we are asking information, right? So questions are not considered as a proposition. Remember this point. 2 plus 3, what is 2 plus 3? We don't have anything equal to, right? So it is not a correct propositional, right? Solve the equation 2 plus x equals to 3, 2 plus x greater than 8, right? This is also not a proposition. We cannot say whether it is true or false, right? These are also examples of non-propositions, okay? So please remember this important point that questions cannot be considered as a position, okay? Now, what about the logic part, propositional logic part? There are two important points. These are the important points you need to understand. Okay. So first thing is that propositional logic is called Boolean logic, as it works on 0 and 1, right? That is what we have discussed. 1 stands for true and 0 stands for F, right? In propositional logic, we use symbolic variables to represent the logic. We can use any symbols for representing propositions such as A, B, C, D, P, Q, R, right? So we can use any alphabet or any symbol to represent a particular sentences, and based on that we can use some connectives, or we can infer something from those things, right? But we are just generally using the variable to store the sentences in this particular variable. Okay, so we'll discuss with the examples, don't worry. So the propositionals can be either true or false, but it cannot be both. So we have discussed this. Propositional logic consists of an object, relations, functions, and logical connectives, right? So propositional logic can be consist of object, relations, or functions, and logical connectives. So it's a very important point, logical connectives. So we'll discuss that. So these connectives are called as logical operators. So if you remember in the last lecture, we have discussed and, or, right? This is not, implies, bi-direction, implication. So these all are the logical operators, right? So proposition and connectives are basic element of a propositional logic. Yes, a proposition formula which is always true. Remember this, which is always true is called as tautology, and it is also called as valid sentence, right? So when I say 2 plus 2 equals to 4, this is a valid sentence, right? Because it is always true, right? So this is true. We know that this is tautology, right? A proposition formula which is always false is called as contradiction, right? For example, 2 plus 3 equals to 4. This is also proposition, but this is a false proposition, and it is always false. That's why we call it as a contradiction, right? The statement which are questions, commands, or opinions are not propositions. Very, very important point. The statement which are questions, commands, or opinions are not propositions, such as where is Rohini, how are you, what is your name. So we have discussed this type of questions. So these all are not the propositions. So please remember this thing, right? So I hope you got the overall idea of what is proposition, right? So here you can see there are different connectives. So connectives can be said as logical operators which connects the two sentences. So what are the logical operators? We have discussed in the last lecture. That is and, symbol is this type. Then or, right? That is we. Then we have not. It is not, not. Symbol is like this. Then we have, or in some cases it is like this also, it depends, but it is not symbol. Then we have implies, okay, that is like this or like this also, right? Then we have bi-directional, that is bi-directional operator, the bi-directional implication, so we can say like this, or it represent like this also, right? So bi-directional implication, right? But in or there is one more thing, that is basically a exclusive or, right? Exclusive or, so that is basically a XOR, and XOR is represented by like this, in a circle there is a cross symbol, right? This is XOR, right? So I hope you understand the particular okay, I hope you understand this particular logical operators. We'll discuss this one by one. Okay, now first, what are different types of propositional logic? So syntax of propositional logic defines the allowable sentences for the knowledge representation. There are two types of propositional logic. Okay, so first one is atomic proposition and second one is compound proposition. So what is atomic proposition? As name suggests, these are the simple proposition. It consists of single proposition symbol only, right? These are the sentences which must be either true or false, right? For example, uh, today is Monday. That's it. That's the atomic proposition. Only one sentence is there, right? Today is Monday. That's it. For example, we can say today is Monday, right? That's it. We cannot say anything, right? But what is compound proposition? Compound proposition are constructed by combining simple or more atomic proposition using parentheses and logical connectives. This is more important, and logical connectives. For example, I can say today is Monday. Today is Monday, and I am going to Goa, right? Today is Monday and I am going to Goa. That is basically compound proposition. So today is Monday, this is atomic proposition. I am going to Goa is also atomic proposition. But when we when we combine these two atomic proposition by using the logical connectivities, that is and in this case, so we can say it is a compound proposition. Okay. So I hope you understand the example between atomic proposition and compound proposition. Okay. Right. So next, let us discuss about the logical operator. So first one is negation. Right. So what is negation? Suppose P is any proposition, the negation of a P is this. Right. This type of symbol we use to represent negation of a P. Meaning of negation of P is false. Suppose P is true. Okay. If P is true, then negation of P will become false. Right. So when I say P equals to today is Monday, right? Today is Monday. Then negation of P will become today is not Monday. Today is not Monday. So it's basically a negation of this particular statement, right? I hope right? So I hope you got this particular example. So here also you can see John does not love CSE, right? So suppose our P is John does love CSE, right? 191. But here you can see the negation of this particular P will be John does not love CSE 191. Okay. Note that negation of P is a new proposition generated from a P. Yes, this is a new proposition which is generated from a P. So our P is today is Monday, but our negation of P is become today is not Monday. So this is the new proposition which is generated by a negation of a P. Okay. So we have generated one proposition from another proposition in this case, right? So we call this negation symbol we use to generate a new proposition, and this is called as negation operator. So please remember this is a negation operator, right? This type of, or in some cases we will use like this also, or like this also, okay? But this is a negation operator generally widely used, okay? So I hope you understand this particular example of negation, okay? What is negation in short? So we'll discuss this with the help of examples also. So in general, we can define logic operators that transform one or more propositions to a new proposition. So negation is a unitary operator since it transforms one proposition to another, right? So because it just works on atomic propositions, so that's why it is unitary operator. We'll see a few binary operators also like and or in the upcoming slides, and they transform two propositions to a new proposition. So in the previous slide we have discussed that I use AND operator to join two atomic propositions. Okay. Now, generally we use truth table for this particular purpose. If we want to verify our conclusions. So, what is truth table is? So, truth table lists all possible combination of the values of the operands and gives the corresponding values of the new proposition. Okay. So basically, when I say P is my true, so so P is true, right? So in that case, negation of P will become false. When I say P is false, then in that case, my negation of P will become true. Okay. So it's very important truth table. You can just note it down. Okay. So all the truth tables are very important in this case. Okay. Like for during this particular uh, propositional logic. So it is very important. So you have to remember those things. Okay. Now when then we have conjunction, that is basically AND operator, right? So now we introduce a binary operator that is basically a conjunction, and that is AND operator, which corresponds to AND, right? So P and Q is true if and only if P and Q both are true. Okay. So this P and Q will become true. P and Q will become true only when P is also true and Q is also true. Then we can say P and Q are true. Okay. So this is a truth table to verify that. So when P is true, Q is true, P and Q is also true. So here you can say P is false and Q is true. Then we can say P and Q is false, right? So this is a truth table. You need to understand this. And also, if you consider as this P and Q and this P and Q, and if we consider false as 0 and true as 1, so it basically says 1 1, that is 1, or 1 and 1 is basically 1, right? So 1 and 0 is basically 0. So 0 and 1 is basically a 0, right? 0 and 0 is basically 0, right? So this is what AND operator is. In short, we can say P into Q. For a Boolean thing, you can say P into 1 into 1, 1, 1 into 0, 0, 0 into 1, 0, 0 into 0, 0. So this is what Boolean algebra is in terms of 0 and 1, right? But you can just remember this truth table, nothing much more complex. You already have learned this in your 11th and 12th. Okay. So I hope this is clear to everyone. It is conjunction. Okay. So we'll move on to a disjunction, that is OR. Okay. So another binary operator is disjunction. This is indicated by a V symbol, which corresponding to OR, right? But the slightly different from the common use. So we can say P or Q is true if and only if either P is true or Q is true or both of them are true, right? So this is basically a condition for inclusive OR. So there are two things. First one is exclusive OR, and second thing is inclusive OR, right? So we are discussing about the inclusive OR. Okay. So this is basically an inclusive OR, right? In inclusive OR, what we do, P or Q is true if and only if P is true or Q is true or both of them are true, right? So here you can see the truth table. P is true, Q is true, then it's P or Q is also true. And here you can see true or false, it is true. False or true, it is true. False or false, it is false. Right. So this is basically a truth table. And this we call as inclusive OR, right? Now, same thing, if I just want to represent this in terms of Boolean algebra, so what I can say, uh, 1 so 1 plus 1. So in terms of OR, we generally refer as plus. Okay. So 1 plus 1, that is 1 in Boolean algebra. So 1 plus 0, that is 1. So 0 plus 1, that is also 1. And 0 plus 0, that is basically 0. Right. Here you can see this is the output TTTF 1110. Right. So this is in terms of Boolean algebra, but you need to remember this thing only, that is truth table. Okay. So I hope you understand this disjunction means it is inclusive OR. Okay. What is inclusive OR here? So we'll discuss about exclusive OR also, but yeah, I hope this is clear to everyone. But looking at the truth table of and OR operator, what we can conclude, okay? Now just look at this truth table of AND operator, right? Even when any of the proposition, like either P or Q are false, then we can say my P and Q will be false, right? Here you can say either any of the statement P or Q is false, then we can say my P and Q is basically a false statement, right? But here in the case of OR condition, if any of the P or Q is basically true, then I can say my P or Q is basically true, right? Only both the proposition P and Q are false, then only we can say P or Q are false. Okay, so this is a different bit. So this is the difference between OR and AND operator. So please remember this point. Okay, you just need to compare it. That's it, right? So we have discussed about inclusive OR. Now this is what exclusive OR is. So it is inclusive OR, so it allows both possibility as well as either of them will be true, right? So either A is true, either B is true, or both are true, right? Either A is true, B is true, or both are true. Then the statement value is true. But what happens in the case of exclusive OR? Only allows one possibility. So either if A is true or B is true, then and only then the value of this proposition will be true. If both A and B are true, even the statement's value will be false, right? This is what true. So this is what exclusive OR is, and it's indicated by this particular symbol, that is plus inside the circle, right? So actually this operator can be expressed by using these specific symbols, right? And it is same as negation of P bidirectional implies Q. Okay, so we'll discuss this, but as of now, just remember P inside the circle, that is plus symbol, that is basically a exclusive or we can say NOR also, right? Or we can say XOR also, right? And also in some cases we also represent like this P V, then we have underline it and then Q. So this is also symbol of exclusive OR. Okay, so either we can use this or this. Okay, both are the symbol of exclusive OR. Okay, so please remember that. And so please remember that. So what is truth table here? So P and Q is true, then P exclusive OR is false. Okay, this is very important thing. If both the propositions are true, then the output will be false. If both the propositions are false, then output will be false also. So in this case, what we can say, in order to be P exclusive or Q should be true, either P or Q must be true, right? Either P or Q must be true, then only we can say P or Q will give me a true value. Otherwise, it will give me a false value. If even if both are true, still it will give me false value, or even if both are false, still it will give me a false value. Right? So if you compare with the previous slides, so here you can see true or true is basically true in the case of inclusive or, but true or true is basically a false in the case of exclusive or. Okay, so please remember this very important point. It may ask in the exam about this inclusive and exclusive or. Okay, so I hope you understand this particular concept. Okay, now about the implication. So it another binary operator, this is basically implication indicated by a symbol, this arrow, or in some cases this is also a symbol of implication, right? So how to read this? P implies Q correspond to P implies Q. It means that if this car costs less than $10,000, then John will buy, right? So if this happens, if P happens, then Q will happen, right? If P happens, then Q will happen, right? This is basically a P implies Q, right? And if you see the truth table here, so when both P and Q are true, so we can say, okay, P implies Q are true. If P is true and Q is false, then we can say P implies Q is false. But remember this two point, okay? When P is false, it means we can say P implies Q, right? So if P itself is false, then in either of the cases, either Q will be true or false. It must be a true. It will be a true, right? So this is what the truth table of implication is. Like if P is false, if this particular P is false, then we can say the P implies Q will always be true, right? So in this case, only one condition is that is false is basically when P is true and Q is false. This is also important thing you need to note. Okay. Now we'll discuss few important points regarding the implication. So implication represents a structure of if P then Q, right? This is what if P then Q. That is P implies Q. So P is basically a statement having it is raining and Q I am indoors, right? Then P implies Q will become what? It means if it is raining, then I am indoors, right? So in case of P implies Q, P is the antecedent P is antecedent and Q is called as consequent. Okay, so Q is called as consequent and P is called as antecedent. So please note this point because very important. When the antecedent is true, the whole implication is true. In the case that the consequent is true, right? If it is raining and I am indoors, then sentence if it is raining, then I am indoors is also true, na? Right? Right. But when the accidental is true, the implication is false. If the consequent is false, that is, if I'm outside while it is raining, then the sentence if it is raining, then I'm indoors is also false, right? So this is what we have discussed in the truth table. Here you can see true implies false is basically a false value only, right? Now, however, when antecedent, that is basically a P, is false, then implication is always true regardless of the consequent, right? So this is what we have discussed in the truth table. Here you can see whenever the P is false, whenever the antecedent is false, right? And whenever the antecedent is false, then our P implies Q will always be true. This is more important point. Right? This is what at this point discussed, right? This can be sometimes be a confusing concept, but you need to understand this. Whenever my antecedent is false, that is P is false, then the implication is always true. That is P implies Q is always true, right? So regardless of the consequent, right? Right? And there's one more case when the antecedent is false, that is P is false, right? So logically we can't learn anything from the implication when P is false, right? Because if this particular condition is only false, then what we can conclude from that particular thing? Nothing, right? So looking at our example only, if it is not raining, the implication doesn't say anything about whether I am indoors or not, right? I could be indoor type and never walk outside even when it is not raining. This is possible, right? Or I could be an outdoor type and be outside all the time when it is not raining. So when our antecedent that is P is false, we cannot conclude anything, right? So in that case, what we can say? So when the antecedent is false, we say implication is trivially true. Okay. So whenever the P is false, we can say P implies Q is always true, right? This is always true, right? So this is what we have discussed in the truth table. Whenever the antecedent P is false, we can say P implies Q is always true irrespective of the value of Q here, right? So please remember this truth table, very important for exam point of view. And these are the reasoning part of it, right? From that particular truth table. Now, there are few terminologies which can be used in the implication. So, because implication statements play such an essential role in mathematics or in AI also, a variety of terminologies is used to express P implies Q, right? So, if P, then Q will happen. Q if P, P only if Q, P implies Q, P is sufficient for Q or Q is necessary for P, right? Q follows from P. So, with all these things can be inferred from this particular implication, that is P implies Q. Okay, this is what we are reading it. So this terminology also we can use, like if P then Q, Q if P, Q is necessary for P. So all those things, so all these terminologies we will be using, right? So please keep a note of this very important point, right? Now let us look at a particular example of terminologies for implication. Suppose our proposition P is Alice is smart and our proposition Q is Alice is honest. So what P implies Q will give us, right? I can say if Elias is smart, then Elias is honest, right? So same thing I can say that Elias is smart is sufficient for Elias to be honest. Elias is honest if Elias is smart, right? This is what P implies Q, right? If Elias is smart, then Elias is honest also, right? That is what P implies Q is. Same Q implies P. So that Elias is smart is necessary for Elias to be honest. Elias is honest only if Elias is smart. Okay. So P implies Q or Q implies P, right? So we have discussed both the condition, but the main important thing is that these terminologies we are used to represent the P implies Q, right? And Q implies P in this case. Okay, so please go through this particular example carefully and try to understand it, right? By using these terminologies. Okay. Now next is bi-directional implication, right? So another binary operator is called as bi-directional implication, denoted by this particular symbol. Okay, like this also sometimes both the direction, like there is an arrow in both the directions, right? This is what P bi-directional implication Q is. Now corresponding to P is true if and only if Q is true. You can see this truth table, right? If P is true, Q is true, then P bi-directional implication is true. But P is true and Q is false, then it is false. P is false, Q is true, it is false also, right? But both are false, then it is Q, then it is true, right? But what we can conclude from this, right? P if and only if Q is true, right? So P is true if and only if Q is true. So this is basically a truth table, and this is what we say. P is true if and only if. This is the main thing here. If and only if Q is true, right? This is what bi-direction implication is, and it's very important truth table also, right? For example, here you can see a student gets A grade in CSC 191 if and only if his weighted total is greater than 95%, right? Student will get A grade in particular subject if and only if his weighted total is 95%, right? So I can consider this as Q and this is as a P. So I can say P bi-directional implies Q, right? So this will be a sentence for that, right? So I hope you understand what this bi-directional implication is. We'll discuss the examples also, but these truth tables are very important. Okay, so what is bi-directional implication now? So it is an implication that goes both directions. You can read it if and only if, and you can read it as if and only if. So that is P if and only if Q, right? So it's the same as P implies Q and Q implies P taken together. This is also a very important point to note, right? So P bi-direction implication is basically a P implies Q and Q implies P. Okay, this is very important point. For example, let us take the same example. If P it is raining and Q I am indoor, then P if and only if or bi-direction implication say means that if it is raining, then I am indoors, and if I am indoors, then it is raining, right? So this means that we can infer more than we could with the simple implication. But if P is false, then Q is also false, right? If it is not raining, we know that I am also not indoor, right? So kindly go through this particular truth table, okay? Okay, so this is very important part now, this precedence of operators, okay? So if we are given some expression to us, so this precedence is very important. This is not operator, right? So the precedence of not operator is highest, then and, then or, then and, then or, then implies, and then bi-directional implication, right? So similar to our board mass, right? In mathematics, similar to board mass, it is the precedence of this particular operator is there, right? For example, if you take like this example, like negation of P and Q, it means that first we'll perform the negation of P and then we'll perform Q, right? Here also P and Q, then implication are it. So according to this precedence, first and operator will be performed, then we can use implication here, right? So please note this particular table, very important exam point of view. So I hope you understand this particular concept of propositional logic and various operators, right? Various operators and their precedence, right? So we're going to discuss few examples based on that. So that will be enough for the gate exam, right? So there is one homework for you guys, okay? One homework condition. So Suppose for example I have negation of P in bracket P and Q, and I am saying it is equivalent to negation of P and negation of Q. Okay, so try to prove this. First take P, then Q, then P or Q, then negation of P or Q, right? Then consider negation of P, then negation of Q, and then negation of P and negation of Q. Okay, so these are the six columns you have to. So these seven columns you have to consider for this particular combination, right? True, false, false, true, and false, false. Okay. Now just try to complete this particular truth table. Okay, you can just comment below, right? Or if you're on my particular, or if you're using my website, so you can just directly post a screenshot of this particular table. Okay, so this is very important. Okay, so you need to fill this particular blank space. Okay, so what will be the value of P or Q? Then negation of P or Q, negation of P, negation of Q. And what I'm saying, these two are equivalent, so try to see whether this and these columns are equal or not. Okay, so that's it from this particular lecture. Thank you.